So the big one we're going to be looking at is boiling point. So if we look at something like CH3OH versus CH3CH3, so here we have methanol, here we have ethane. So when we look at boiling points, physical properties, what we have to think about is what's going on in the bulk, right? So that's where we're looking at intramolecular interactions. So is it ionic-ionic? Is it hydrogen bonding? Is it van der Waals? Is dipole-dipole? Is it van der Waals? Okay, and as we go down that list, the attractive forces in the bulk become less, right? So ionic-ionic is going to be the tightest. So often ionic compounds will be attracted to each other really strongly. What that means is that those tend to have really high boiling points or even be solids. When we go the opposite direction, when we go down to van der Waals, then all of a sudden we're getting down to things that have very, very weak intermolecular interactions. And so therefore they seem to be gases, right? So therefore their boiling points will be really low. So if we look at these two, so that's one is intermolecular force. The other is the size of the molecule, right? The actual just how big it is. So if we look at these two, they're relatively about the same size. If we look at its total atomic weight, they're about the same, right? It's not drastic difference. So in this case, right, the difference is going to be intermolecular forces. The third thing we're going to look at is kind of surface area. This is more important as you go down to van der Waals, right? So let's look at a few and talk about, and I'll talk about what the differences are. So here we have about the same molecular size. If we think about it, there's not much these two molecules can do except be two carbons with some hydrogens around, two atoms with some hydrogens around it. And so of the things we're looking at, both of these have about the same molecular weight. They have about the same shape. The difference here is going to be our intermolecular forces. Over here we have something that can hydrogen bond, so that intermolecular force is going to be hydrogen bonding. Over here we have no ionic, no hydrogen bonding. Do we have an atom that is more electronegative, like a chlorine or a fluorine or bromine? No. So this one really just falls down to van der Waals, right? So weak attraction between the molecules based on an instantaneous dipole. So between these two, then this one is going to have the higher boiling point. Right. And methanol is a liquid at room temperature. It will turn to a gas, not much over that, but at room temperature it is a liquid. If we look at ethane, well, ethane, we're not familiar with that one, but propane has 3 carbons, and propane is what's in propane cylinders, right? It's a gas. So ethane is even smaller. It's going to be a gas. If we think about methane, methane is a gas, right? It's a natural gas that's in the gas lines. So when we look at these, right, that's what we're going to be comparing. The other thing we can compare on these, again, is the size. So if we look at something like propane, keep adding too many carbons. Sorry, I just realized I need to just go simple for now. Okay, so if we look at these two molecules, this one is propane. Okay, this one over here is heptane. right? In this case, we don't have ionic, right? So that's going to be the strongest. The thing we need to look at is first, do we have ionic? Do we have a hydrogen bonding? No hydrogen bonding atoms. Do we have a dipole moment? No heteroatoms, right? So therefore, these two are all just carbons and hydrogens. So that gives us the van der Waals. So both of these have van der Waals. So therefore, if we're looking at this, at these two and comparing, then we're going to look at the size. Right? And so of course, this one is much larger. This one is actually a liquid at room temperature. This one is a gas. Propane, we just talked about that one, is propane cylinder, right, is a gas. This one is heptane. Heptane is one of the multiple molecules that's in gasoline, right? So as we get up to that point, it's liquid, but it doesn't take much for gasoline to vaporize, right? So it's not like it's a huge difference, even though we've added 4 carbons, right? We're not talking about something that's really big. If you get to carbon 14 up to 20, now you're getting to really thick stuff. Now you're getting to asphalt, right? You're going past diesel into asphalts when you get up to about C20, right? And so you can kind of see what's happening. But even asphalt, what do you notice on a hot day on an asphalt street? Right? You see the little vapor sign. Part of that is heat, and part of that on a new street is actually some of the molecules actually coming off. Not something you probably wanted to hear. Then if we look at so let's look at 1, 2, 3, 4, 5, 6, 7, 8. All right, let's look at that one, and let's look at this one. Okay, here we both, starting at the top, right? We're comparing these two. Both of them have van der Waals. Nothing else. We don't have any heteroatoms, don't have any charges, no dipole moments. And then if we look at our size, both of them have 8 carbons, so they're about the same size. So on this one, we're really going to be looking at how well can these interact, right? So the bigger something is, right, the more interactions you could have, right? So that's the difference between propane and the heptane. But then all of a sudden here we have 2 things with 8 carbons. Now it's not the actual overall number of carbons, but it's still the potential interactions between these two, okay? If we look at these two, which one looks like it would probably be able to have better interactions with another molecule of itself? The simple octane or the 2,2,4 trimethyl pentane? The simple one, right? And so this thing to think about this one is think about trying to put boxes together, right? Or trying to, you know, if you moved and you're packing up all your boxes, what's the easiest set of boxes to carry, right? Boxes that either fit inside of each other or are exactly the same size, right? Whenever you start to have things that are different sizes, so let's say that you are packing to move in and you put all the stuff in there, once you start to, if you put like one thing that's a different shape in there, it just doesn't fit. And if we look at the 2,2,4 dimethyl, it's kind of odd, right? It has this shape over here, right? Where one of these is going to have to be coming out at you, right? The other one's going to be going back at you. Over here too, right? We have the hydrogen. So it's going to be an odd shape. So when we start to get to branching, right, it's going to give us a lower boiling point. Now this isn't always a hard and fast rule, but it is the most often. There are a few cases where you can get branching that they actually will pack tighter. Okay, that's not very common. So when we're looking at physical properties, specifically boiling points, the things you need to look at are intermolecular forces. That's your first thing. So the question would be, which of these 4 items have the highest boiling point? You would look and see which one has the highest energy intramolecular force, right? Does any of them have ionic? Do any have a dipole, right? And then you would look at, are any of them a different size, right? So if one is much bigger than the other and they all have equivalent intermolecular forces, then you'll go with size. Now, intermolecular forces has a bigger impact than size. So if you have something that is a couple of atoms bigger, but you're comparing a dipole to van der Waals, or especially hydrogen bonding to van der Waals, right? The hydrogen bonding is going to win out in that case. Okay, so let's try a few of these. I'll put some atom molecules up here. You tell me which one is got the highest boiling point. So in the first one, the first series, we can start by looking at the intermolecular forces. So the first one, what type of intermolecular force will it have? Okay, it's got hydrogen bonding. It doesn't have ionic, but it does have a hydrogen bonding oxygen-hydrogen, right? They're easy to determine because there's only a few atoms with hydrogens on them that can have hydrogen bonding. In the second one, right, what do we have here? Okay, here we have a dipole moment, right? It's not balanced. There is a dipole moment. There is only one chlorine. So therefore we have a dipole moment. So this would be a dipole-dipole interaction. And then the last one, we don't have any heteroatoms, right? It's all carbons and hydrogens. It's all balanced. So therefore this is only going to have instantaneous dipoles, so van der Waals. So if we looked at these, right, this one is going to have the highest boiling point. Right? This one will have the lowest boiling point. Right? Right? And then, of course, the dipole will be in the middle. All relatively similar sizes, right? Okay, let's look at the next three. Any questions about these first three? Next three. Okay, as we look at these three, okay, one of the things we haven't covered yet, but is very important, is to realize that your group 1 metals are always charged, right? So if I see a sodium, a potassium, or lithium, just go ahead and put a positive next to it, and whatever's next to that, put a negative, right? So if you ever see OLI, right, the oxygen is going to be negative, the lithium is going to be positive, right? This is a standard conversion you can do anytime you see these. So anytime you see a sodium, lithium, and potassium, think those are positive, whatever's next to them must be negative. Okay, so therefore this one then will have ionic-ionic. Okay. The one in the middle, does it have hydrogen bonding? No, there's no hydrogen attached to the oxygen. Does it have dipole? Yes, it does have a dipole. It does have two bond dipoles. Are those two bond dipoles opposing each other? No. So therefore it has a molecular dipole. If it has a molecular dipole, then we're going to have dipole-dipole. And then the last one, no heteroatoms, all carbons and hydrogens. We're going to have van der Waals. So here we get the opposite direction. The highest boiling point is over here. You can do a similar thing with melting points, but for most of our organic molecules, we're going to be looking at boiling points, not because most of them are going to be van der Waals or dipole moments, which are weaker. Yes, ma'am.
And then one of them was like much bigger that kind of heated it up, made the same like boiling point, like similar.
Yeah,
So
you'll.
Well,
Ionic is a lot stronger, okay, right? So you would have to have a much, much bigger hydrogen bonding molecule, right? If you were looking at, let's say, dipole, and van der Waals, there your difference doesn't have to be as big because the difference between the strengths is significant. But let's say we had 4 extra carbons on the van der Waals, then the boiling points might be equivalent. If it's 1 or 2, no, the intermolecular. If you're talking about ionic, you might have to get to really big. So let's say C4, a C20 carbon, right, versus sodium pentoxide, right? So that's just 5 carbons and an oxygen. That's a solid. But C20 is still kind of a flowing liquid. You know, asphalt's not solid, right? It's not boiling, but it's kind of a, well, it's a goop, right? And so if we look at those two, right, there we have a much bigger group that behaves more like a liquid, and we have a smaller one that's a crystalline solid, right? And so, but if you're looking at dipoles, you're usually looking at 4 or 4 carbons or more before you start to flip. Yeah. And that's usually pretty obvious, right? One's much bigger than the other one. Yeah, but when you're looking at ionic, that one is such a stronger strength that those are almost always solids. Okay, other questions? All right, let's go ahead and move on into the next chapter. So this, you'll have some homework over this, and really just go down that list. Right? Recognize if there is an ionic, if it's hydrogen bonding, if it's dipole, if it's van der Waals, and then look at some of the variations such as branching and such, okay? The next we're going to look at is stereochemistry. So here we have 2 compounds that have the same molecular formula. They have the same connectivity, right? The same atoms are connected to the same atoms. We're not connected in the same spatial arrangement. These 2 molecules are chiral. Okay. If we look at these 2, right, this bromine coming out at us, we have a hydrogen going back, bromine coming out, hydrogen going back. Okay, what we have here is something like this, right? We have handedness, and that's where chirality really comes from. We're talking about handedness, left-handed, right-handed, right? And if we look at it, except for a ring on that finger and a scar over here, right? These 2 are mirror images of each other. Right? So in chirality, what's happening is we have a spatial arrangement that makes handedness. So if we look at this molecule here, and if we look at this molecule compared to that molecule, we can see that those are mirror images of each other. If we took and looked, right, this bromine is coming out at me, that bromine's coming out at me, this hydrogen going back, that hydrogen's going back, I have a carbon up here, carbon, right, carbon, carbon, and just like if I held up my hand to a mirror, right, I would see my other hand. That's what we're talking about, mirror images, right? So I cannot superimpose one of these on top of the other, just like I can't do that with my hand, right? I can't take my hand and go and put it like this, right? But if you took somebody else's left hand and they lined their left hand up with your left hand, right, they would superimpose, right? And if you were out of phase, so if we go Star Trek and we say out of phase, right, they could actually put their left hand inside of your left hand and they'd be about the same, right, if you had the same size. Right, so that's what we're talking about superimposing, right? Is there any way that we can take these two molecules and rotate them in space and have them line back up, superimpose on top of each other? If not, they are chiral, right? And of course, they're stereoisomers, right? So stereoisomers, so stereochemistry has to do with stereoisomers. So remember, isomers, we're just looking at things that are same except for their spatial arrangements. If we looked at these molecules, so let's take this bromine and then over here, we take these two versions, right? What happens if I spin this one? Well, if I spin it, I'm going to end up with this, right? So these two are equivalent. So here I can superimpose them. So since I can superimpose them, these two are the same molecule. So in stereochemistry, we're looking at the spatial arrangement of the carbons, not just their connectivity and not just their chemical formula. So we're going from constitutional isomers, right, up. Now we're going to things that have spatial arrangement. To have a stereocenter, we need a position where we can have differences, right? One of those is if we look at a double bond. If we look at these two, they have the same connectivity, but they do not have the same spatial arrangements, right? This one over here, they're both on the same side. This one is known as a cis. So this would be cis 2-butene. That is a stereoisomer of trans 2-butene. I'd have to break that pi bond to get these to rotate into each other, right? Their connectivity, how the atoms are connected are the same, but where they are connected in space is not the same. So which atoms are connected to which are the same, but how they're spatially connected is not the same. That's a little bit different than chirality. Now, chirality is a form of a stereocenter, but it has to do with a three-dimensional space. If we look at these, and the way that we can determine that this could be a chiral center is that we have 4 different things attached, right? If we look at this, we've got an ethyl, and that's the abbreviation for an ethyl, right? We've got a methyl, We have our bromine, and we have our hydrogen. So we have 1, 2, 3, 4 different things attached. So if we think about a carbon with 4 things attached, that's going to be a chiral center. So what are some of the rules that have to go along with that? What does the carbon have to be? What hybridization? It's got to be sp3, right? It's got to be sp3 to be a chiral center. If the carbon is a chiral center. There's also something called non-atom chirality, such as there's a few examples of that. Maybe I'll show you one later, where it's chirality in space. It's 3-dimensional, but there's not a carbon that's the center of the chirality. It's in space. Okay, so we have to have a carbon that's sp3. What about sp2? Well, sp2 can still be in a stereocenter, right? But it's not going to have a chirality center. So a little bit different. Okay. The other thing we need to do is have 4 different groups. Why do we have to have 4 different groups? Well, let's take a slight different look at a molecule. Let's say we're looking at this version. Well, in this version, right, we changed that. We added a carbon to one side. Now what I have is I don't have a mirror plane between the two. I actually have a mirror plane bisecting the molecule. If we look at what's on the left and the right side of that mirror, they are identical. I can say that here's a carbon, there's a carbon, right? The bromine is being bisected by the mirror. The hydrogen's being bisected by the mirror. I have a methyl here and a methyl here, right? So every atom has a mirror plane through the molecule. So because of that, there's not a chiral center, right? This has got symmetry through the molecule. Therefore, since we look at this one over here, these two are the same molecule. Even if we drew this one, what would happen if I spin that? I get this actually the same thing, right? Because when I spin it, I have an ethyl on one side, ethyl on the other side, I spin it. So there's a couple of things you want to be looking for chiral centers, right? One is 4 different things at a chiral center. You can tell that there's a potential for a chiral center if there are 4 different groups attached. If we look down here, we could have determined that that wasn't going to happen, because if we look at what our molecule is, I've got an ethyl, right, on that side, but I also have an ethyl on this side. So that would have predicted that I would have a plane of symmetry. The other is finding a plane of symmetry, right? So if it's difficult for me to figure out what's looking for, I can find a plane of symmetry in the molecule. Okay. We know that these two up here do not have a chiral center, even though they are stereocenters, but they're not chiral centers because they have a plane of symmetry, right? What's the plane of symmetry here? The paper, right? These are planar, so therefore I can take that as my plane of symmetry, and so therefore these can be bisected by that plane of symmetry if you line all the hydrogens up on the methyl groups, and therefore they don't have chirality. So if you can bisect something with a plane of symmetry, it's not going to have, it won't be a chiral molecule. If it does not have 4 different things attached to a carbon, it's not going to be a carbon-based chiral center. So let's look at a practice problem. Here, just identify okay, so identify the chiral centers. Okay, and what you want to look for here is 4 different things attached. When you're getting started with this, it's really a good idea. And notice it hasn't gone very far from adding our hydrogens to not adding our hydrogens. But step back. I know it's been a long time, a whole week, but step back a whole week and add all your hydrogens in. That's going to help you on these, especially when you're getting started. Later, you won't need it, but right now, this is a good way to get started. Now that we have our hydrogens in, can something have 4 different groups attached to the carbon if it has more than 1 hydrogen? No. Okay, so anything that has more than 1 hydrogen is by that rule, right, not going to be a chiral center. So in carbon compounds, I can eliminate a lot of potential possibilities really quick. Anything with 2 hydrogens or more is not going to be a chiral center. So then that has me looking at what things do have chiral centers or only have 1 hydrogen. So let's take a look at this one right here, right? So 2 hydrogens, 2 hydrogens, 2 hydrogens, 2 hydrogens, no chiral centers. Here, it only has 1 hydrogen. So then what we need to do is look at the other things that are attached. Okay. We can go here and here. These 2 both have CH2s, right? But this one only has a CH. So therefore I know this one is different than these 2. On this one, I can go out 1 more, right? This one only has a CH-CO, right, bond. This one has a CH2. So therefore I know that all 4 things around this are different. That's a chiral center. You can also see that visually, right? But you can also step it out like that. This one's pretty easy visually. Sometimes you even, when you got years of practice, you still need to step it out. Okay, so we have 1 hydrogen here, so we can look there. CH, CH2, CH2, so we know that one's different than these 2. Are these 2 different? Well, we go here and we see the CHO. Over here we have the CH2, so yes, that one's all 4 different groups. So there's a potential there's a chiral center. Okay, our next hydrogen is over here. So we have an oxygen, we have a CH2, CH2, right? Now we go CH2, CH. So those 2 are the same. These 2 are the same. Are these 2 the same? Are these 2 the same? Where are we now? We've circled all the way around and we've reached the same point. What does that mean about this side and this side of that center? They're identical, right? And if you can think about it, we should be able to draw, if we could change this in space, we'd see a mirror plane going right through there. So that means that this center is not a chiral center. Okay. The next one out is the hydrogen here, right? We've got a methyl, we got an ethyl, and we have the carbonyl. Does that make that a chiral center? Yes, 4 different things. That's a chiral center. Can the carbonyl be a chiral center? It could potentially be a stereo center, but it can't be a chiral center. Okay. Because it's sp2, it's not going to have 3-dimensional spatial arrangements. It could potentially. The carbonyl, as shown, doesn't have a stereo center, but let's say that I added a hydrogen up here let's say it was a protonated carbonyl, then it could be a potential stereocenter, right? So potential, right? But it won't be a chiral center. Okay, so this one here is the one that would have caught you, right? You would have seen one hydrogen and you would have just gone directly to chiral center. Okay, got to check and make sure. If I had a methyl group over here, that would have made each half of that different, right? And that would have made this a chiral center. But since both halves were the same, that's not a chiral center. This is one of the things you'll have to do, is just recognize chiral centers as you're going through these. And the best way to do that is to step yourself through it. Now, if we have two molecules that are the same, well, that are not the same, right? We need a way to differentiate these two. We need a way to figure out that these two are not the same molecules. And so right now they're both 2-bromobutane. Okay, so what we use for that is R and S. R is going to be right-handed, S is going to be left-handed. So R is going to be clockwise, S is going to be counterclockwise. And it's based on a priority numbering system based on the atomic mass. So if we look at this molecule, bromine has got the highest atomic number. So that's going to be 1. Hydrogen has the lowest. It always has the lowest. So it'll be 4. Then we're going to look, and we have a carbon and a carbon, carbon and a carbon. This carbon is attached to 3 hydrogens. So the way we look at that is we have a carbon that is attached to 3 hydrogens. And then the other carbon, so let's call this carbon 1. Carbon 2 is attached to what? Well, it's attached to a carbon and 2 hydrogens. So because of this carbon here versus that hydrogen, that makes this 2, and that makes this 3. So with the lowest priority back or away from you, then what we're going to do is we're going to look at the direction of the brom 1, right, to 2 to 3. So we're going to be looking at this direction. So 1 to 2 to 3 with 4, the lowest one being back. We know it's back because it's got the dash mark signifying it's behind. So if it is going clockwise, right, that's going to be R. So that means this one up here is going to be R2-bromobutane. Now, in most cases, just like this one, right, the hydrogen's not shown, so you've got to draw it in. Don't not draw it in because it'll you need to verify that it's black. If you've got 2 in the plane, right, this is in the plane and that's in the plane, and you got 1 coming out at you, that means the hydrogen that's not shown is going to be behind, right? So if we look at this one, here we have again 1, then the ethyl is going to be 2 because it's attached to another carbon. And then the methyl, it's not size, right? It's not the size of the ethyl, it's the fact that that first carbon is attached to another carbon. That's going to be important if you look at branching later on. Sometimes students will say, well, that one's much bigger. You could have a smaller molecule that has branching early on that would have a higher priority than, right? So you go 1 carbon, next carbon, next carbon until you find a difference. And the priority goes to the one that has the more atomic number. So if something is attached to another carbon or if it's attached to 2 carbons. Okay, so 1, 2, 3, 4 is back. Okay. So we look, we go now 1, 2, 3, right? That is counterclockwise. Okay, so that is sinister. And the first original sinister just meant left-handed, and all of a sudden it became like sinister, like villain type thing, but it's not. It's just left-handed, sinister. I find it's easier for y'all to remember S and R if you remember that. Sinister is left-handed. At one point, they tried to make left-handed people do things right-handed so that they weren't shown to be right-handed because they were superstitious about people that were left-handed. Although in the elite squadrons of Greece, they were all left-handed because everybody else was right-handed. So if you had your shield, shield and you're right-handed, if you do it the opposite way, all of a sudden, when you're going to fight somebody and they have their shield up, your hand is coming in the opposite direction of where their shield is supposed to be, so you actually have an advantage. So there you go. Hope that helps you remember R and S and you don't get them backwards. Okay. So, all right, so that's how that works. Okay, let's try a few of these. Before we try a few, what happens then if I had shown, this molecule, okay, with the bromine back? Do what? Right, so what we have to look at is what do we do with this one? So the hydrogen in this case is coming forward. So there's a couple of ways to do this one. The book probably has one. What I like you to think about here is where should you have been, right? So in this one up here, right, these two, I'm on the right side of the piece of paper. On this one, where should I have been? On the other side of the piece of paper. So let's say you had a transparent clock face and you're watching the clock, right? So sometimes you'll see these in train stations and stuff, if you've ever been in a train station. And you walk up and you're looking at it from the wrong side. What's odd about that? The hand is going the wrong direction, right? It's going counterclockwise versus clockwise. You just happen to be on the wrong side. So the way that I prefer you to think about these is to go ahead and put your priorities. So 1, 2, 3. My lowest priority is here. Go ahead and go 1, 2, 3 in that direction, right? And 1, 2, 3 in that direction is what? That's counterclockwise. But then where is 4? If 4 is back, you stay. If 4 is forward, it's not S, it's R. Because I'm just looking at it from the wrong face. What most books will tell you to do is to redraw it. I'm not a big fan of redrawing because redrawing can cause mistakes. So if you're looking at it and you find your rotation, right? So we're going R and the lowest priority is back, I stay R. If I find S and the lowest priority is at me, it means I'm on the wrong side of the paper, so therefore it's not S, it's R, right? So it's just the opposite. The lowest priority always has to be back away from you, but if you draw it here and it's forward, it's not a problem. The problem comes whenever you have it in the plane. if you're in the plane, now you've got to think about this. Which side of the paper am I on? Well, you're actually in the paper, right? And that's hard to visualize, and it's not as easy as just flipping one side to the other, right? I'm not on the wrong side of the paper, right? I'm in the paper, and that's hard to visualize. So for this one, you're gonna have to redraw it, okay? But it's important to know how you redraw. For this to redraw, right, I have to change 3 things. I need to rotate, right? If I only change 2 things, what could I be doing? If I change 2 things, I could change the structure from one thing to another, right? If this had been R and I just switched 2 things, I could draw an S. So if you only switch 2 things, you're gonna be in trouble. So what you need to think about is I'm spinning this, I'm rotating it. So if this was my axis here, I'm gonna rotate this one, and it doesn't matter which way you rotate it, but let's go ahead and rotate it that way, right? So let's rotate this way. What you should do is draw, and here, very specific, redrawing gets you in a lot of trouble. Okay, so be specific about this. Draw your methyl going to your bromine going to your hydrogen going to your methyl. Then draw your structure and follow your diagram. Where did the methyl go? The methyl went forward, right? Where did the bromine go? The bromine went up. Now it's in the plane, but most importantly, the hydrogen that was in the plane now is back. Okay? So double check, okay? The methyl was back, the methyl is now forward. The bromine was forward, now it is in the plane. My hydrogen was in the plane, it is now behind, okay? This is a correctly redrawn molecule. Now I can go in and do my ratios, right? So I have 1, 2, 3, 4. Doesn't matter if the hydrogen is back or forward, right? Just as long as it's back or forward. If it's in the plane, I need to redraw it. So therefore 1 to 2 to 3, this is going in the clockwise direction, so that's right. And where's my lowest priority? Lowest priority is back, so it stays R. Yes. Do what? It's a methyl. Yeah, so this one is attached to another carbon, right? Okay. So priorities are based on atomic numbers. Once we have the priorities, we figure out if it is R and S. We figure out whether it's clockwise or counterclockwise. And then we check our lowest priority, right? If it's back, we stay where we are. If it's forward, reverse it. If it's in the plane, you're gonna have to redraw it and do it again, okay? So let's try a couple. It's always helpful to find the chiral center to start with. Then you can start naming it. Okay, it's always a good idea to go ahead and show your hydrogen. Then we're going to look at our priorities. So that's going to be 1. Then I have 2 carbons. So I'm going to call this carbon A and carbon B. So carbon A, carbon B. Carbon A is attached to a carbon and 2 hydrogens. Carbon B is attached to 3 hydrogens. Okay. So that gives me carbon A ends up being 2, carbon B ends up being 3. So 2, 3. I go 1, 2, 3. That's going to be the S direction. Where's my lowest priority? It's back. So I can state S. It's not necessary to underline the S. I got a habit of doing that over 30 years ago. So after doing my check, I always underline the answer. Don't have to do that. That's just for the tendency I have to show that I've checked. Okay, questions about the first one? Okay, let's take a little bit more time to do the second one. And we put in our hydrogen. We look at our first carbon, A, it's only attached to 3 hydrogens, right? It's a methyl. We look at B. B is attached to 1 carbon and 2 hydrogens. And then if we look at C, now we have a double bond. So what do we do with the double bond if we need to have it attached to 3 things? So if it has to be attached to 3 things, right, then that means this carbon is attached to what? Is that carbon attached to that carbon how many times? Twice, right? And then a hydrogen. So for this, we're saying that that double bond is attached to 2 carbons and then a hydrogen. So then if we look at our priorities, then this is going to be 1, 2, 3, and then the hydrogen will be 4. So let's put that on here. So C was 1, B was 2, A was 3. I go from 1 to 2 to 3. That is clockwise R. Where's my lowest priority? My lowest priority is back. So this is R. Okay. Now, if we were going to name this, right, this one is going to be R 3-methyl cyclohexane. Oops. And again, remember the ene of that has to be the 1 and the 2. So that makes it 3-methyl. Over here, we have the alcohol. We'll get into more alcohol naming later, but this is going to be S2-pentanol. And again, practice through it. Just as you're learning to do this one, just do it step by step, nice and careful, and you'll get them right. Next one to look at is what happens if we have 2 chiral centers. So let's look at bromine. Bromine. I'm going to go ahead and put my hydrogens in. Again, most often the hydrogens aren't shown, but it's helpful as you're learning this to put your hydrogens in. Just to, so first, let's go through and see if we can find chiral centers. So carbons that have 4 different groups attached. Okay. So at this position, it has a bromine, a hydrogen, methyl, and then it has this group with the bromine attached. Are those 4 different ones? Yes. So there's one. Okay. And of course, that one's the same, bromine, hydrogen, methyl, and then the ethyl with the bromine attached. Over here, we have chiral centers, right? Chiral center, chiral center, chiral center. Here, chiral center, chiral center. Now, the other thing we can look at, right, is do we have a mirror plane? Do we have a mirror plane that bisects any of these atoms? In the first one, can we draw a mirror plane any direction, right, that would bisect this molecule? No. How about this one? Could we draw a mirror plane that would bisect the molecule? Yes. Right, so I can draw a mirror plane right there that bisects the molecule. That makes this an achiral molecule. So if you can bisect the actual molecule, it's not a chiral molecule, it's an achiral molecule. So here I have chiral centers, but the molecule overall is achiral. When something is achiral, the molecule is achiral, it means it's not going to have a mirror image. So if we look down here, it also has a chiral center, a mirror plane bisecting it. It's achiral. Can I superimpose the top one on the bottom one? Can I take this one where the bromines are out and this one where the bromines are back? Right, because there's a mirror plane, I can superimpose these. These two are actually equivalent. We can't draw a mirror plane in the other set, but we can draw a mirror plane what? Between the two, right? So these two are mirror images of each other. So it kind of goes kind of like that. Right, there's a mirror plane there. If you can find a mirror plane between 2 molecules, those are called enantiomers. Okay. Up here, when we first did these over here, these would be known as enantiomers. Okay. Over here, since it has chiral centers, but is an achiral compound, this is known as a mesocompound. To get the last type of stereo naming system, we need to change one of the bromines to something else. So let's do this again, but let's change one of the bromines to a chlorine. Now, if we look for mirror planes in these four, can we have a mirror plane bisecting any of the four versions? Can we have a mirror plane here now? No, we've got a chlorine and a bromine, right? Here, chlorine, bromine, here, chlorine, bromine, and also they're on opposite sides of the plane. So therefore, we don't. Can we have a mirror plane between the molecules? Will this reflect into that? Well, yes, if I rotate it the right way, those two will reflect. How about these two? Yes, if we think about this being the mirror plane, so if we kind of rotate it down and look at it from the top, these two are mirror planes. So therefore, all these two are enantiomers. These two are enantiomers. But what is this to that? Is this one a mirror plane of that one? No. Okay. Whenever you have chiral molecules that are not mirror images of each other, those are diastereomers. So that would mean these two are diastereomers. That would mean these two are diastereomers. And that would mean those two are diastereomers. So in this case, we have two sets of enantiomers, right? And we have four sets of diastereomers. In the previous one, right, we had enantiomers. We would have also had diastereomers. Going across top and bottom. And then we'd have, actually, this is gonna bother me. My OCD is coming out. These two are enantiomers with that one. Remember, they're all the same. I mean, diastereomers. So these two are diastereomers with that molecule. It's the same molecule. Okay. Okay, so enantiomers and diastereomers. What is an enantiomer? It's a mirror image of itself, right? So it's a mirror image. Diastereomers are the same connectivity, but not mirror images. And then meso compounds are achiral molecules, meaning I can bisect the molecule with a mirror plane. Sorry, I didn't know that was up there. Not mirror images. When you're looking at structures like this, it's pretty straightforward. What is an enantiomer and what is a diastereomer? When you get to more complex molecules, I think one of the ways I suggest doing that is going ahead and naming it as RNS. So practice, get good at RNS, and let's name it. So let's take this set here and name these and then look at them. And actually, so that it's not as easy, normally we draw zigzags for our molecules. So let's do it this way. And then let's use the naming system to figure out where our enantiomers and diastereomers are. Because of the time, I'm going to go through this pretty quick. So we have 1, 2, 3. So that's going in the counterclockwise direction. My lowest priority is back. So this is S. What was the question? Oh, I'm going wrong. I'm going the wrong direction. Thank you. 1, 2, 3. That's R. All right, lowest priority is back. If we look at the chlorine side, the chlorine gets 1, then this is 2, 3. Let's go in that direction. That is R. But where's my lowest priority? My lowest priority is forward, so this should have been S. So this one is R and S. Well, for time, we don't have to do that one over again. We already know what that one is. That one's going to be R. We do the chlorine. Here, we're going to go 1, 2, 3. So that is R. Where's my lowest priority? It is back, so it stays R. So this is RR. Over here, we're going to go 1, 2, 3 in this direction. So that is R, but where's my lowest priority? It's forward. So that would actually be S. We know that one's R from the previous one. And again, you should take your time doing this. I'm running out of class time. So, and then here we have the bromine. Again, so this one's going to be S, and this one's going to be S. So we have RS, SR, RR, SR. So now we have those named. Now when we look back up here, I'm going to go ahead and name these, right? So we can see what those were. That's an R, this is an S, this is an R, this is an S. For the chlorine, we have 1, 2, 3, that is S, so this is R. 1, 2, 3. This is S, S, and R. Okay. Now notice in the original one, and then we'll go to the bottom one so you can see what I'm talking about. In the original one, what happens when I have enantiomers? What happens to my chiral centers? I switch both, right? So I switched the R for the bromine for an S with the bromine. And then for the chlorine, I switched the R to an S. So I switched both chiral centers, and those are enantiomers. Here I went RS and SR, right? So those are enantiomers. What happens for diastereomers? I only change one, right? I've changed an RR to an RS. Okay. So therefore, when we look down here, which of these are enantiomers and which ones are diastereomers? Well, these are our enantiomers, RR to SS. And if we look up here, there was actually the other opposite set, the left-handed set versus the right-handed set. Yes, sir. Which one? This one, RR? I rotated right here. Yes. Yeah, but it's rotated differently. See the methyl group? Okay, I zigzagged it down here, right? Up here, I drew it as kind of the U shape. Okay. So what that means is this molecule, right, and this molecule aren't the same. This molecule and that molecule are the same. Okay, so naming it, these two are the same molecules. These two are the same molecules. Okay, by rotating around there, right, I took that chlorine and that was back, and I'm now had to go forward here. By rotating around that bond, I took the chlorine that was forward, and now it's going back. Okay, and you're going to see the zigzag more than you'll see the U, and we'll talk about that a little bit on Monday. It was simpler, so I decided to delay on that. Okay, so if we continue, look, these two change, so those are enantiomers, right? And then all of these versions are diastereomers. And one last thought while we're here, what happens if we have the bromines? If you notice with the bromines, this is SR and RS, but what's the difference? All of the substituents around each of the different chiral centers are identical. So if I have an RS and an SR, and all of the groups, I have a bromine, a hydrogen methyl, bromine, hydrogen methyl, they're all the same, then that's a potential meso compound. An SSRR can't be a meso compound, but an SR could be if they're all the same. If they're not all the same, then they're another set of enantiomers. Okay. All right, we'll get some practice up for this. This will be on the test next week, so I'll get some homework going on it, and we'll finish up later.